Hello, my name is Daniel Nenni, and I'm the founder of SemiWiki, the open forum for semiconductor professionals. Since going online in 2011, SemiWiki.com has registered more than 200,000 active members. If you're not a member of the community, please register as my guest. I hope to see you there. Today's webinar is titled Issues in Data Storage, Cybersecurity, Data Privacy, AI, Boot Storage, IoT, and Mission Critical Data and Autonomous Driving. The speaker today is Steffen Allert. He heads the global sales organization of Hyperstone. If you have questions, please use the question tab and we'll answer them during the Q&A at the end of the presentation. Okay, let's get started. Over to you, Steffen.
Thanks, Daniel, for giving me the opportunity to present today. I'm happy to become part of the SemiWiki community. This webinar focuses on addressing issues in data storage and is intended to provide value and insights for everyone curious about data storage. I have been in the industry for over 20 years, supporting customers in their decision for storage media. Over the years, I have learned how important it is to have a deep understanding of customer requirements and technological challenges in order to provide an optimal solution. Here is a quick glance on where Hyperstone sits in the value chain, so you can best understand where our expertise comes from. We develop flash controllers and firmware, working together with integrated device manufacturers. These are the folks creating SSDs, micro SD cards, and many other storage devices for a range of use cases and markets. These markets have different demands and their systems' unique requirements. So the IDMs work closely with us and our engineering teams to fine-tune our controllers for their specific needs. This webinar is all about how to avoid pitfalls when designing a storage module. All too often, we see companies investing in the wrong solutions and experiencing an array of issues later down the track, as their storage module wasn't designed for their end application's use case. We want to share our experience with you on how to get the best possible solution for a given use case. How can you achieve that? What questions should you be asking? There is more to a storage system than meets the eye. I find this image powerful in highlighting the major issue we see all too often. We only see what's obvious, but not what lurks below. What really defines an optimal module that's geared towards your use case? Let's get into some aspects that are more than often overlooked. Usually, the driving factors for a decision are performance and price. With performance, I essentially mean speed, and with price, the cost per gigabyte. But there's more under the waterline. Understand your application's use case and reliability demands. Where will this storage module be integrated? Into what kind of an application? How much storage do you really need? Will it be reading or writing data? Is it in operation 24/7 or only occasionally? Have you considered the true value of your data in relation to security or potential power failures? If your company was hacked or a power outage resulted in a loss of data, how bad would that loss be? Furthermore, have you considered longevity and supply? Realistically, how long should your end application be in operation for? Are you looking for long-term chip supply, for example, 7 years or even more? Or is 2 years before components are EOL'd okay for your application? And finally, where are you willing to trade off? You have heard of it before. You can't have it all. To achieve the optimal solution, you must be prepared to make sacrifices for unnecessary functionality, which in turn allows you to optimize other features. There is no one-size-fits-all solution in our industry because each use case is different and requires specific decisions in many parameters. Here are some examples of different applications with unique use cases. Let's take the industrial robot as an example to explain some of the trade-offs that can save you money and optimize product quality. Usually, a robot operates 24/7 and boots rarely. It logs data, meaning it frequently writes small data chunks. Sometimes, in an emergency situation, the robot has to be shut down immediately. In this case, the robot needs to save all relevant operational data to enable a successful reboot. Hence, the storage media needs to survive a hard shutdown. Now bridging to the trade-offs for a robot working 24/7 while writing small data chunks that are wearing down the storage device. You need high endurance. Endurance in the storage world refers to the lifetime of a storage device that is defined by the number of program erase cycles of the NAND flash. By aligning the desired lifetime of the robot and the storage device, you can minimize your costs. If a robot has to reboot for the first time after 7 years of operation, the storage media has to have high data retention. Data retention refers to the number of years after which data can safely be read. Again, by aligning the desired lifetime of the robot and the storage device, you can minimize your cost. Additionally, endurance and data retention are correlated, meaning that data retention decreases as the number of program erase cycles increases. For this industrial robot use case, you need to consider a combination of both. Finally, to protect the robot against sudden shutdowns, countermeasures can be taken. On the robot side, this can be done with capacitors. Alternatively, on the storage device itself, it can be done by implementing intelligent firmware features. With firmware features, you can avoid expensive capacitors at the cost of a small performance penalty. These were just a few of the many trade-offs tailoring a storage media to a use case. This can get complicated really quickly, and some expert knowledge is definitely helpful. In fact, you can define 3 synthetic use cases that can be found in any combination with the applications discussed in the slide before. Boot functionality, where the OS is read once and a very few data writes take place. Second, sequential read and write. Simply speaking, streaming or recording videos. Random read and write. For example, updating databases like your CRM. And in reality, you always find a mix of those use cases. But there are other important factors to ensure quality of service of a storage device. Those are temperatures, high, low, medium, desert, mountains, vibration, different in a railway than in a standard solution where no vibration is there, removability, power fail robustness, fit rate, defective parts per million, mean time between failure, lifetime monitoring and failure analysis, serviceability. As an example, and I touched that already, high temperatures influences data retention negatively. And if because of vibration, you choose a non-removable solution, your lifetime service model needs to be adopted. Here are some key questions you should be asking in the following order when choosing a storage device. Let's start with compatibility. You should identify which storage interfaces your main processor offers to connect storage. Next is performance. What performance do you need? And be aware, datasheets only show theoretical best case performances, and more often, steady-state performance is more relevant. Then we come to selecting your flash. Different flash technologies impact performance, as does density. And how about security? Will your system need security features like secure boot, data encryption, or access control? Later comes the topic of trade-offs. Very likely you will be faced with conflicting requirements. You need to define your most important parameters. And last but not least, consider support. What level of support do you expect during the life cycle of the product? Different stages might require different support levels. Here we have an illustration of a generic module with 8 different aspects that interweave. Like discussed, you should be asking the right questions and understand how these aspects impact and interweave with one another. For example, the selection of flash impacts reliability, lifetime, performance, and price. So, if price is key for you, you need to choose the lowest flash quality, thus reducing lifetime and reliability. Let me briefly dive into a specific use case. Traditionally, NOR was used in boot devices to ensure fast and reliable boot performance, meaning the booted device was initialized and operational within a predefined time. With other storage types like eMMC, this was not possible. However, with specific measures in the firmware, a reliable and fast boot time is possible. Having said that, if you want to replace NOR in a boot storage with more affordable options like eMMC, you need to understand the use case and tweak the controller firmware the right way. This is another example of how knowing your use case can save you money. To summarize, know your use case, speak to an expert, and educate yourself. It will ensure you achieve the lowest total cost of ownership. I hope this webinar got you started, and if you want to find out more, you can visit the download area of our homepage to gain access to our white paper series, which goes into depth on an array of topics related to the fundamentals of reliable flash storage. So thank you very much for listening to this webinar. And if you want to get in touch, feel free to send us an email or find me over on LinkedIn. And I'm happy to answer all questions which might have come up during the presentation. So let's get started with the Q&A session.
Thank you, Steffen. This is a great presentation, and there are some questions. First question is, what do you mean by flash quality?
That's a good question. And this comes down to the technology. So we have different technologies which are used in NAND storage. So this is SLC, which means single level cell, MLC, which means multi-level cell, TLC, which means triple level cell, and there are even more. This reflects the number of bits stored in one single cell of such a NAND array. SLC only stores 1 bit, so you only have a status of 0 and 1. In MLC, you store 2 bits, which already is reflected by 4 different states. So from 0, 0 to 1, 1. And in triple level cells, it makes it even more complicated. You have 3 bits resulting in 8 different states. And all that together makes the flashes less reliable and reduces the lifetime because the size of these little cells are the same. And if you can imagine storing more data in the same physical size, makes the storing and the retrieving more complex. And by thus, you also reduce the quality because of the less or the higher probability of a wrong data retrievement out of the cells. So that means SLC has the highest quality, but is also associated with the highest cost. On the other side, there's TLC, which is low cost, but the quality is much less. But there is a way in the middle. And these are the pseudo modes of these kind of products. So for TLC and MLC, you can have a pseudo mode simulating an SLC flash in a TLC NAND. And as TLC flashes, even if you only use it as a pseudo SLC, so instead of 3 bits, you only store 1 bit, still the cost is much less because the basic technology is lower. And it's a very good compromise when you are in a situation that you have to have a certain amount of cost limitation, but you also need a certain amount of reliability. And this selection is key for the quality and the lifetime of your system. And we could go into much more detail, but it might take an hour to explain all the details. I'm happy to do so, but maybe not in this webinar.
Great. No, that's a good answer. Another question, can you explain in a bit more detail what you mean by power fail robustness?
Yeah, of course. Power fail robustness is something which is key for industrial applications or applications where systems can fail, systems do fail, but they have to come up immediately after the power is back on the system. So that means and requires certain measures on the controller side and on the firmware side to ensure that when you go down, when the power goes down, the data which is on the drive is still valid. So the key word here is data integrity. So the controller has to ensure under all circumstances that under all power fail issues or solution situations, the data on the drive is always valid again. Because if this is not the case, the boot process afterwards would fail and the whole system would not come up again, even if power is back. So power fail robustness is a very important issue, for example, for production facilities. Systems can fail, they are exchanged, but then afterwards the system has to come up immediately without or with the lowest delay possible. And there, valid data integrity is a key word and a key solution, a key feature to make that happen.
Oh, got it. Another question, how is your approach different to mainstream products?
Well, for example, eMMCs have been developed for mobile and our focus, mobile applications like mobile phones, and our focus is on industrial and telecom. This is very different. And together with our IDM customers, who all focus on different markets and applications, eMMC need to be and are optimized for different use cases. So a use case in the industrial arena in an industrial automation plant is different to a base station somewhere around creating the mobile infrastructure for a mobile network. And the requirements have to be reflected in the firmware so that we can, or the customer and the solution can cope with the different setups, the different situations which can happen during operation. So we do not turn a consumer product into an industrial solution. We develop an industrial solution from the very beginning.
Yeah, I understand. Final question, Steffen. Why do you believe longevity impacts lifetime cost?
Well, this is a very good question. It might not be obvious to see the reason behind that and the answer behind that. But longevity means that the product is available for long years. I talked about 7 years or more. Our products are in the market for 10 years. We even have products which are in the market 20 years. And if you use those products in a solution, you can use them for that time period, 10 years. And you don't need to requalify. So that means you avoid requalification costs. And if you assume the consumer time, or the time of EOLing products in the consumer space, which is happening every 1.5, 2 years. This would require 5 requalifications in a 10 years period. And just imagine the cost associated with this requalification. So you need to have sample components. You need to qualify them. There might be some problems. You have to solve those problems. And all of this is associated with costs. And many people oversee that at the first part. And this is one thing which lurks under the waterline of the iceberg picture I've shown before.
Great. Thank you, Steffen. Thank you for your time. Excellent presentation. And thank you, everyone, for participating in the SemiWiki webinar series. And have a good day.
Thank you very much from my side as well.